Real Numerical Algebraic Geometry by Jonathan D. Hauenstein, Dhagash Mehta, Margaret H. Regan, Samantha N. Sherman, and Charles W. Wamper. I'm Dr. Samuel Allen Alexander, mathematician and philosopher, still here, and I'm reading this article, which was published in 2025 in the notices of the AMS. The authors are hosting an AMS-sponsored mathematics research community on real numerical algebraic geometry. The research program developed by the authors will focus on theory and algorithm design for real numerical algebraic geometry, along with solving problems arising in applications such as kinematics and chemical reaction networks. This article provides some background and an introduction to the themes of this MRC. Interested pure and applied researchers in mathematics and fields related to the applications are encouraged to apply. Well, of course, it's past now. This came out in 2025. Real numerical algebraic geometry. Numerical algebraic geometry is the mathematical subject area focused on numerically computing and manipulating solution sets to systems of polynomial equations. The name numerical algebraic geometry was coined in 1996 in a paper by Soames and Wamper. By performing computations over the complex numbers, which is algebraically closed, one can prove many results regarding polynomial system solving, leading to computationally feasible algorithms that can be implemented using floating point arithmetic. For example, one can compute the irreducible components of the solution set of a given polynomial system and represent it on a computer via a so-called numerical irreducible decomposition with witness sets. Several books provide a general overview. For most applications of polynomial systems in science and engineering, only real solutions are of interest. Some examples include computing the equilibrium of a dynamical system, synthesizing a mechanism to perform given tasks, and reconstructing three-dimensional models from two-dimensional images in computer vision. Of course, if a polynomial system has only finitely many solutions over the complex numbers, then one approach is to compute all of the complex solutions and retain only the real subset of solutions. Although such an approach has been used effectively on problems of modest size, the number of real solutions are typically only a very small fraction of the number of complex solutions, so much computation is wasted. For example, a problem in 4-bar synthesis has only 384 real solutions out of 8,652 complex solutions, while a problem in computing equilibria of a dynamical system has only 2 equilibria out of about 10 to the 18 complex solutions. Whew! Thus, a key research area is to develop numerical approaches for computing and manipulating only the real solution set to a system of polynomial equations yielding real numerical algebraic geometry. Since the real numbers are not algebraically closed, much of the theory underpinning techniques in numerical algebraic geometry no longer holds when considering only the real solutions. However, there is a growing body of algorithms for numerically computing and manipulating the real solution set to a system of polynomial equations. This includes critical point methods for sampling real points, routing functions and roadmaps for deciding connectivity, and cell decompositions to provide a full description. Figure 1. A curve traced by a Griffiths-Duffy platform and exceptional Stewart-Goff platform. Exploring the real parameter space. Polynomial systems arising in science and engineering typically depend upon parameters such as reaction rates, lengths, and temperature. Since the behavior of the real solution sets can change as the parameters vary, one can explore the parameter space to determine the different behaviors. One tool for exploration is a parameter homotopy of the form h of xt equals big F of x semicolon t times p0 plus 1 minus t quantity times p star equals 0. Moving from t equals 1 to t equals 0 deforms the parameters p from the starting parameters p0 to the target parameters p star. A parameter homotopy allows for efficient computation of solutions to big F of x semicolon p star equals 0 for many different parameters p star. Such information can be used to provide insight into the geography of the parameter space. Figure 2 presents a decomposition of the parameter space based on the number of real solutions when the lengths of two legs of a 3RPR mechanism are changed. The color represents the number of real solutions, such that the darker the color, the more real solutions there are. The boundaries correspond with the discriminant locus. Figure 2. Parameter space decomposition for 3RPR mechanism based on number of real solutions. If one performs a real parameter homotopy inside of a connected component in the complement of the discriminant locus, then there must be a bijection between real solutions for the start and target parameters. Parameter space exploration coupled with learning the boundaries has showed that corresponding real parameter homotopies significantly decrease the computational cost of computing the real solutions, especially when the number of real solutions is small in comparison to the total number of complex solutions. For example, in the trifocal posed geometry problem illustrated in Figure 3, there are a total of 312 non-singular isolated solutions, yet only about 35 of them are real on average. Computer vision showcases minimal problems where the number of real solutions is drastically smaller than the total degree. Therefore, continuing to expand current methods to focus on just real solutions can have a large impact on efficient and fast solving for many parameter instances within applications. Figure 3. Trifocal posed geometry. 3 pinhole cameras view a point plus tangent. When using a sequence of parameter homotopies, it is natural to consider what happens to the solutions when one performs a loop in parameter space and returns to the original set of parameters. Classically, the monodromy group encapsulates all the possible permutations of the isolated solutions. A simple example of a non-trivial monodromy loop is demonstrated using the complex square root via big F of xt equals x squared minus t equals 0. As shown in Figure 4, starting at the pair xt equals the pair 1, 1 and tracking the solution x of t for t equals e to the I theta as theta goes from 0 to 2 pi will return to the pair xt equals the pair minus 1, 1. Thus, the monodromy group is the symmetric group on two elements since the two solutions x equals plus or minus 1 and t equals 1 can be interchanged. Let's look at Figure 4. Figure 4, monodromy loop. As t circles in the complex field around 0, x interchanges between 1 and minus 1. Although the monodromy group captures some structure within the solutions over the complex numbers, it can fail to capture interesting behavior about the real solutions. For example, returning to the 3RPR mechanism whose parameter space decomposition is provided in Figure 2, a non-trivial monodromy action corresponds with a non-singular assembly mode change. This is important for engineers to understand when controlling parallel manipulators due to the possible change of pose at the home position. Although the complex monodromy group is the full symmetric group, the 6 real solutions in the red region actually break into 2 subsets of 3 that can only permute amongst themselves. In particular, starting with a home position pose, it's possible to return to 2 other poses. Since this behavior is not captured with the classical monodromy group over the complex numbers, this exemplifies the impact of having methods that focus on the real numbers to understand the behavior of the real solutions. For positive dimensional real solution sets, sampling techniques combined with topological data analysis can be used to build graphs that approximate the topological structure. For example, Figure 5 shows the configuration space of a parallel 5-bar manipulator, which can be used for path planning to efficiently connect different configurations while avoiding configurations that are problematic from a mechanical perspective. Figure 5, path planning and configuration space for a parallel 5-bar manipulator. In addition to sampling, other approaches for numerically computing positive dimensional real solution sets include cell decompositions and decompositions using routing functions, which will be explored as part of this MRC. Number of real solutions. A natural question to ask of any parameterized system with generally finitely many complex solutions is the minimum and maximum number of real solutions. For example, assembling a Stewart-Goff platform corresponds with solving a parameterized polynomial system which generically has 40 complex solutions. In 1998, a set of parameters was found such that all 40 solutions are real, meaning that the corresponding Stewart-Goff platform robot can be assembled in 40 different ways. Similar questions arise in many applications areas, including parameters for a chemical reaction network to have multiple real equilibria. Another example is to determine the maximum number of equilibria for the Kuramoto model, which is a mathematical model used to describe synchronization. With 3 oscillators, the maximum number of real equilibria matches the generic root count over the complex numbers, namely 6. With 4 oscillators, it was conjectured, using parameter space exploration, that the maximum number of real equilibria was 10, which is strictly smaller than the generic complex root count of 14. This upper bound of 10 for 4 oscillators was proven in reference 15, with Figure 6 illustrating the approach which computed at least one sample point in each component. The cases with 5 or more oscillators remain open. Figure 6, parameter space decomposition arising from n equals 4 Kuramoto with sample points in each component. A very pretty picture. A natural question concerning parameterized families is whether there always exists a real solution, i.e. if the minimum number of real solutions is positive. Of course, if there's an odd number of non-singular complex solutions to a polynomial system with real coefficients, then there is always a real solution since non-real solutions rise in complex conjugate pairs. For problems with an even number, the answer can be quite challenging. This is relevant, for example, in computer vision, in which one may want to determine if there always exists a real reconstruction given any location of the image features. An open problem in real enumerative geometry is to determine if there always exists a real plane conic that passes through the origin and intersects each of 6 given real lines. Over the complex numbers, there are 18 such plane conics generically, and all experimental evidence to date suggests that at least 2 of them are always real, while a proof remains elusive. An instance of this problem is shown in Figure 7. Figure 7. Real plane conic intersecting 6 given real lines and passing through the origin. The origin is green. The plane itself is the shaded, it sort of looks like a rectangle, but that's just because they're doing just a piece of it. Software. Software packages implementing various numerical algebraic geometric algorithms include Bertini, Home for PS2, Homotopy Continuation.jl, NAG for M2, and PHCPack. Paramotopy provides efficient methods for parameterized polynomial systems using Bertini. Some examples of software in real numerical algebraic geometry are Bertini Real for computing a cell decomposition of curves and surfaces, Polytop for computing topological information of real surface, and hypersurface regions for computing complements of an arrangement of real hypersurfaces. And then there's an invitation to their event that they're throwing. I will skip that since the event has already passed. This has been Real Numerical Algebraic Geometry. I'm Dr. Samuel Allen Alexander. Please like, comment, and subscribe. I'll see you in the next video.